Okay, hello again. Now it's time for us to cover the next topic, one sample t-test. So now we're getting into some real tests that you can conduct on real data that you collect. As I'll point out in a moment why you can't really use the z-test as often. It has to do with what you know about your sample versus the population. It comes down to variance. Do you know what the variance of the population is? Usually you don't, and if that's the case, then you can't use z typically. So I want to get into a test statistic today, the one sample t that really is one that you're going to be using depending upon your hypothesis. So basically, the one sample t-test implies you only have one sample. Okay, so you're not comparing two groups to each other. You're not comparing group A and group B, or group A versus B versus C. You're not doing that here. This is even more basic than that. This is when you have one group, group A, and you're comparing their performance on some measure with a criterion of some kind, a criterion level. Let's say you're comparing them to chance. Okay, let's say that you just have one class that you're grading exams for, and you're not comparing them to another class. Rather, you're just comparing their exam grade with the 60% passing criterion. Okay, that's what you would need a one sample t-test for. Okay, and I'll give you another example of that as we continue through the lecture for today. So all test statistics, also called inferential methods, because again, you're trying to infer something about the population or parameters of the population based on your sample and your statistics for that sample. All these test statistics like Z and T and F we'll get into later in the course, they all have some things in common. They all use descriptive statistics like mean and standard deviation. They all use probability. And really they all have the basics of hypothesis testing. For example, all have a null hypothesis. All use alpha. Typically it's set at 0.05. And for all inferential methods or test statistics, increasing n, or the sample size, increases the power to reject the null hypothesis. Something important to keep in mind as you proceed through the course is this issue of power. Okay, some things are different among test statistics. For every new test statistic, we will cover 4 topics. I will point out that there is going to be a situation that you need to specify to determine what test statistic you should use, including your hypotheses. The actual test statistic that is appropriate there, your theoretical reference distribution for that test statistic, the critical values, decision rules, and finally the assumptions that come along with that test statistic. And here is the one, here's the information about Z that we've covered before. I encourage you to create a similar kind of chart for each of these test statistics so you can kind of side by side compare Z with T. So what you want to do is put the 4 topics I just mentioned on the left side. Okay, the situation, the test statistic, the distribution for that test statistic, and its assumptions. And the test statistic itself goes on the top. So put Z here, and then on the next slide you can put T over here. So how is Z sub x bar broken down? Well, as we've seen before, we're talking about one sample, just like we are for the one sample t-test. The null hypothesis, based on that hypothesis about IQ, before we learned that the mu for IQ in the population is 100. And so that's your null hypothesis, is that for your sample, it's just going to be, just like the general population, it's going to be 100. Okay, and you can have some kind of alternative hypothesis, but that's not something we're going to state here. You can put it in here if you want, but it doesn't have to be, because your alternative hypothesis can change. Let's see here, the variance here, sigma squared, is known in this case, and this is something that is certainly the case with Z, but not for some of these other test statistics, as we'll see. The test statistic itself is the formula for Z sub x bar. Okay, we've seen that before. The distribution also we've seen before, with a mean of 0, a mu of 0, and a variance of 1. And assumptions here, population is normal, observations are independent. Okay, so we've seen all this before. For the one sample t-test, however, it's a little different here. At the top, the mu equals 100 for the null hypothesis, that's the same. But in this case, the population variance, sigma squared, is unknown, and that's usually going to be the case in the real world. We were able to use Z before because we had a hypothesis about IQ, and for IQ there's so much data out there, we have a pretty good idea of what the mu is in the population. We also have an idea of what the variance is. As I pointed out, it's 225. If you know what it is, then you can use Z, but if you don't know what it is, you got to use a T. Okay. So here's the test statistic. It's a little different than the Z. You take x bar minus mu, you divide by the square root of s squared divided by n rather than sigma squared over n, because you don't know what sigma squared is. You have to use your sample and statistics based on your sample, such as s squared. The distribution for T I will illustrate for you on the next slide, but this is how it's defined. T with degrees of freedom, that's what df is degrees of freedom, equals n minus 1. So the overall number in your sample minus 1. And the assumptions for the T distribution are the same as for the Z distribution. So here's what it looks like. The T distribution has let's see here. It's, well, just like the Z distribution, it's symmetric, it's smooth, it's unimodal, so there's just one mode. The mean, median, and mode are all the same, just like the Z distribution. It has a mu of 0. But unlike, it looks like a standard normal distribution, which I also portray here, but it has longer tails, the T distribution does, and basically it has more variance, okay, more variability. The greater variability in the T distribution is due to the fact that it not only has a mean, x bar, that varies from sample to sample, just like the Z statistic does, but it also has variance, s squared, which also varies from sample to sample. I'll illustrate that a bit later as well. T distributions have only one parameter, degrees of freedom. The formula for this can change from one T statistic to the next, but really the working definition we're going to have for degrees of freedom is goes as follows here. In a sample variance, degrees of freedom equal the number of independent components, usually just n, okay, the number of data points you have in your sample or the number of participants, minus the number of parameters that you're estimating. Okay, so if you're estimating mu, okay, in the population, if you're trying to get an idea of the mean, then that's one parameter you're trying to estimate. The one sample T has the unbiased sample variance s squared in its formula. So think back to what that formula is. You're going to need that in a moment. Formula for s squared. I'm going to have you do some calculations here. The degrees of freedom for the one sample T, as I said, is n minus 1. So maybe you're asking yourself, if you're particularly astute, what the heck changed from the Z formula to the T formula that brought in the concept of degrees of freedom? We didn't have that before for the Z. How does T differ from Z? Well, it has s squared. I guess I did point this out before. Here is the Z formula, and here's the T formula. They're identical, except for this key component here. For Z, you know what sigma squared is, you know what the variance is of the population, but for T, you don't know what it is. So you have to use your sample. You have to try to estimate what sigma squared actually is by using s squared. Okay, and by doing that, you need to use degrees of freedom. So the whole formula for df, degrees of freedom, n minus 1, goes with s squared. It's part of this s squared formula. That's why it's part of the T formula. So keep in mind that there is a T table, just like there is a Z table in your textbook. It's at the back. Even if you're using a different stats textbook, they're almost always going to have a Z table and a T table, and also usually an F table at the back. So anyway, flip open to the T table. It might be Appendix 8.2. So what you're going to see in that table is a breakdown of different T values, and also different degrees of freedom and different alpha levels, 0.05 versus 0.01, and we're going to stick with 0.05 because that's the typical alpha level. Degrees of freedom in rows, alpha for 1 and 2-tailed tests in the columns. Okay, so again, it might be table 8.2 in your textbook. So here's what we're dealing with, very similar to those Z distributions we've seen before, but the critical values are different here. As you might recall, for the Z test, it's 2.65 and negative 2.65 as the critical Z values. But for T, it's a slightly different distribution, so you're going to have slightly different T crit values they're actually 2.26 and negative 2.26. So let's get into an example here, a different one, not dealing with deaf children or IQ. Are people who are interrupted in a task accurate in estimating how long they have spent on the task? So people who were given 20 anagrams to solve were interrupted after doing 10 of them, and they were asked to estimate how long they had worked on the task. The researchers formed a ratio of estimated to actual time, and this, the mu of this ratio, the mean, should be 1 if people are accurate in estimating time. It would be 1-to-1 ratio. They would be estimating the same exact time as what they actually spent doing the task. But of course, it's probably not going to happen. The ratios for the 10 people that you had, so n equals 10 in your sample here, these are their 10 actual ratios. So go ahead and on our system here, pause the video lecture here and calculate the sum of these 10 numbers and the sum of squares for these 10 ratios. You're going to need that in order to calculate s squared, of course. First step is sum of squares, so please do that now. Alright, hopefully you've done that. I'm going to continue. Okay, now compute the mean of those 10 ratios and the unbiased variance and s. Okay, so the main thing you're going to need is mean and s squared here. Okay, go ahead and calculate that. Pause the video so that you can do that. And I will continue now. Null hypothesis, as I said, is that they're not going to be different from 1. Your alternative hypothesis is, your actual hypothesis is that you think they're not going to be the same as 1, that there's going to be a difference in their estimated time solving these problems in the actual time. So if you've done the math, go ahead and compute t, which is x bar minus mu, divided by s squared, the square root of s squared divided by n. And using the critical value decision rule, the upper t crit, as I pointed out, is 2.26. Is the t that you computed greater than 2.26? That's what you need to be asking yourself, because if so, that implies that the p-value is less than 0.05, and you can reject the null hypothesis that they're at 1, okay, that the mean is at 1. Please do these calculations and make this decision before moving on with the lecture. Go ahead and pause it again if you need to do this. Okay, let me continue. So what you do is you find the observed t, the one that you calculated, and the upper t crit, 2.26, in the distribution below that I've pointed out to you. I'm giving away the answer now. The observed t that you calculated is 3.53, and as you can see, it's far off in the tail here, and therefore we can reject the null hypothesis. So your sample of 10 people, the ratios that they give you are not like what you would expect based on your null hypothesis. They're not in the bulk of the distribution. They're way off in the tail, implying that they're quite different. They're significantly different from the bulk of the distribution here. People interrupted in the task significantly overestimated the time spent in the task. If they had been down here, they would be underestimating the time, but they actually overestimated how much time they were spending on the task at hand, the anagram task. And this is how you would write it based on APA style. The ratio of estimated to actual time to solve the first 10 anagrams in the 20 anagram list was significantly greater than 1.0, with a mean of 1.646, standard deviation 0.579, and a t, in parentheses the degrees of freedom, which is n minus 1. Remember, your n was 10, and degrees of freedom for a t is n minus 1, so that's how I got 9, is 3.53, p less than 0.01. So it's not just less than 0.05, it's actually less than 0.01, so that's what you state here. Alright, so what about confidence intervals? We've seen this before for z. You can also calculate confidence intervals for t. Very important that you have confidence intervals. For the problem about the ratio of estimated time to actual time for the anagram solvers, we found the x bar of 1.646. For our sample mean, we know already that x bar is a good unbiased estimate of mu, but we also know that x bar has variability. So it's unlikely that mu is going to be exactly 1.646 just because you have one sample of 10 people that gave you that mean. There's going to be some variance in here. 1.646 should be reasonably close to mu especially if you have a large sample size. Here we only have 10 people, but it should be roughly close. But really you need to see how to get an interval for mu when you don't know what sigma squared is. That's the whole idea here, is you don't know what sigma squared is for t, unlike for z, so you need to get some confidence intervals. Confidence interval for mu gives an interval of values around x bar that are likely to include the true value of mu. So what these are called are 95% confidence intervals, and they're given by this formula here. Very similar to the one I've given you before for z, except again you have s squared instead of sigma squared. So it's going to give you a range of x bar minus t crit. The t crit is 2.262 minus t crit times the square root of s squared divided by n to the positive end of that spectrum. For the problem about that we've been going over here, estimated time to real time, we had these numbers that you calculated, and therefore you get the following confidence interval, 1.23 to 2.06. So, and this is very important, so how do you describe this? How do you state what the heck this means? You do it in one of two ways. You can say that we are 95% confident that the mu, the true mu of the population, of the ratio of estimated to actual time is between 1.23 and 2.06. Or you could say that 95% of the intervals, like this one, like this sample of 10 people, will include the true value of mu of the ratio of estimated time to actual time for people interrupted after solving 10 of 20 anagrams. And so note that 1 is not in the interval, so you reject the null. So the null was that your mu is equal to 1. Well, 1 is not included in this range, so you get you can reject the null here. You cannot reject null if 1 is included here. Let me go back actually for a moment. If you were comparing them to 0, then you would see if this includes 0. It all comes down to what your null hypothesis is. Okay, you had a good reason to use 1, because that would be a ratio of, estimated time to real time, a 1-to-1 ratio. But whatever, it can be really anything you want that is reasonable, and that's what you're looking for in this range. Okay. So let's say that you ran 20 different experiments of 20 different samples of people doing this anagram experiment and getting the ratio of estimated time to true time. You can get the following sets of confidence intervals. And as I said before, you can say that 95% of these intervals, such as 1.23 to 2.06, that's just one of these, will include the true value of the mu of the ratio of estimated to actual time. The true value of this mu is unknown, but many intervals, each from a different sample, should cluster around the true mean. Okay, so each of these lines represents one confidence interval for mu, like the 1.23 to 2.06. Here we have 20 such intervals, one from each of 20 experiments. Only one does not include the true value of mu. Okay, so the true value of mu is here. We're figuring out that it's probably greater than 1. Okay, it's probably somewhere around, what was it here? It's probably somewhere around 1.65. Okay, so we're going to expect that the majority of these 20 experiments are going to have bars that cluster around this mu, if mu is indeed 1.645. A mu of 1 is down here. So you're assuming that mu is 1.645, that you're hoping that your initial, let's say this was your initial experiment that you ran where the confidence interval was 1.23 to 2.06. Let's say that's this one. Well, you're hoping that if you do the same experiment 19 more times, you're usually going to find that the true mu is being covered, okay, is being included in each of those confidence intervals. And here's the one experiment that you ran that didn't include the mu. Well, that indicates that, hey, it's 95%, it's not 100%. For every 20 experiments that you run, yeah, you might have one that does not include the true mu. Okay, that's just indicative of chance. Okay. Another thing to notice here is that the intervals vary not just in position, left to right position, okay, as we've seen before for z, but also in length. Okay, so when I showed you this graphic before for the z-test, they were all the same length. Okay, each line was. They shifted a varied amount from left to right, but they were all the same length. Now that's not the case because you don't know what s squared is. Variance varies from sample to sample for the t-test. That's why this is shorter than that one, and so forth. Some of these are longer than others. That implies that, they have a different variance. Okay, so again, length of each line is variance, and the left to right position is the mean. It's the confidence interval that includes the mean. Okay, so that gives you an idea of how variance and the mean are going to vary depending upon your samples. And that's what the t-test is all about, is trying to determine how similar each sample is to your intended population. Is it significantly different or not? Well, that concludes the lecture for today. I hope that you all now have a better idea of degrees of freedom, the t-test statistic for one sample, and next in the course we'll get into two samples. So if you're trying to compare Group A to Group B, that's quite common. Then you need a different kind of t-test, as we'll see. But for now, this is a basic one sample t-test. So again, post any questions that you might have in the discussion board. You don't have to do this, of course, but feel free to if you wish. You can also email me after you've absorbed all the t-test material if you have any questions. And thanks for paying attention to this lecture.